Welcome to this presentation about the influence of damping factors for coupling applications. So let me give you a short outline of this talk. At first, I would like to give you a short introduction to the functioning principle of Geislinger couplings, especially of Geislinger steel spring couplings. And then I'm going to focus on two different types of these couplings, namely at first a coupling with low friction and after that a coupling with a higher friction. For both couplings we will discuss the main application possibilities and then how to design such special products. And I will also show you some measurement results and a calculation result that will prove the efficiency of these product types. Then a short summary and some additional information will conclude this presentation. So first, let's start with this short introduction to the functioning principle of Geislinger couplings, and maybe some of you already know this. The main components from Geislinger couplings are the radially arranged steel spring packs, which can come in single spring design or multiple spring designs. And these steel springs are then clamped at the outer ring of at the outer part of the coupling with the help of a damping ring, with the help of a clamping ring, and the spring tips mesh into the inner star groove, and this is also where the torque is transmitted. What is more is that Geislinger steel spring couplings they are oil-filled and often have a pressurized oil supply, which means that during torque transmission, when the outer part of the coupling rotates against the inner part, the springs are bent, and this spring bending then causes the oil to flow from one chamber to another via a small radial gap or damping gap. And depending on the size of this gap, the oil flow is subject to resistance, which means that the movement of the outer and the inner part of the coupling slow down, and this effect is then called hydrodynamic damping. What is more is that we have friction, for one between the spring tips and the inner star groove, and second between the springs themselves. And this also causes to slow down the motion of the outer and the inner part, and this is then called friction damping. I'd like to mention that for the next part of this presentation, we will focus on mainly friction damping, and at the end we will talk a little bit about hydrodynamic damping. So, as already mentioned, we talk about these two couplings, one with low friction and one with high friction. And let's start with this low friction coupling, the NCA coupling. This coupling is mainly used for acoustic applications, and the main goal in this field is to reduce noise, which is generated by vibratory forces that travel from the engine to the hull structure and from there on to passenger cabins and so on. And the first path of these forces usually travels directly from the engine to the hull structure, but this path has mainly been eliminated through in the last years through to improved engine mounts, elastic mounts, and therefore the secondary path from the engine via the coupling through to the gearbox becomes more critical, because the gearbox is often hard elastic mounted, and so the vibratory forces are directly carried over here. So one would like to apply a soft coupling. But as we know, in acoustics and sound-sensitive installations, we have sometimes the restrictions, or often the restriction to the permissible vibratory torque that has to be about 3% of nominal torque or even lower. And as we know, the very low vibratory torques and very low vibratory twist angles have a high stiffening effect, a high dynamic stiffness for the coupling, and a stiff coupling is what we wanted to prevent in the first place. So Geislinger had a solution to this problem and invented the so-called NCA coupling, which is a rather soft, torsional, elastic steel spring coupling with very low friction. So the description of this coupling is very similar to the Geislinger description. At first we have the flange connection type, the outer diameter, the width of the springs, the nominal twist rate. And then the last part, this NCA here, tells us that the coupling is, at first it is non-reversible, it has conical springs, and it is especially designed for acoustic applications. So what is so special about this design? So for one, is we used here a single spring design divided by distance pieces. And this means we have already eliminated one main part of friction, because there is no additional friction between two springs themselves. The second design strategy was then to get these springs at the spring tips are slightly tilted when meshing into the inner star groove. That means this tangent on the inner star groove at the contact point between spring tip and groove is slightly tilted by an angle alpha for 0% nominal torque. And this angle alpha is chosen in such a way that for approximately 50% nominal torque, this tangent here is radially aligned. We can see this here in more detail. So here we have this slightly tilted tangent, which is then radially aligned for 50% torque. And this means that the spring tip's movement on the inner star groove consists now more of a rolling motion than of a sliding motion, which means we have less friction at this point. So in order to show you the movement of the springs during torque transmission, we have here for 0% torque, 50, 100, and up to the buffer. And again, here, this is the main part. From 0 to 50%, we see this rolling motion. Yeah, so now in order to show you these properties in some practical manner, we also did some measurements on a Geislinger test rig. This test rig is especially designed to measure very small vibratory torques, also especially for acoustic applications. And on this test rig allowed us to put a static preload on the coupling, and then torsional vibrations were generated by using two electrodynamic shakers. And I would also like to mention that for all of the following test results, we did not measure with a pressurized oil supply, which means that hydrodynamic damping can be neglected, and we only focus for this part on friction damping. So the first main result is this friction hysteresis, as Mr. Hassan already talked about a little bit. We have here the green line is the friction hysteresis, and we have also one red curve which shows one measured friction ellipse, and here we see the dynamic stiffness in this part as this black line. The dynamic stiffness is defined as the ratio of the vibratory torque to the vibratory twist. What we can see here is that for one, this friction hysteresis is really slim and very linear over the whole twist range. And this is due to the fact for this single spring design, and second, due to the fact that the spring tip's movement along the inner star consists now more of a rolling motion than of sliding motion, and therefore it's very slim. This slim hysteresis indicates that for smaller twist amplitudes, the dynamic stiffness is not so much increasing than it would for another coupling. And also this linearity indicates that an increased static preload on the coupling would not affect the dynamic stiffness. So for comparison, we have here the friction hysteresis of a silicon elastomer coupling. What we can see here clearly is For one, it's much broader here, and it has also a clearly progressing slope. And this means that for this broad hysteresis, if the twist amplitudes get smaller, we have a much bigger effect on the dynamic stiffness of the increasing dynamic stiffness on this coupling. And even if there is no low twist amplitudes, there's also this factor of increased static preload, which will increase the dynamic stiffness of this coupling. And so we can see this here very good with this increasing steepness of the measured friction ellipses. We also measured this dynamic stiffness. Here we see the blue line is the measurement of a silicon elastomer coupling, and the red line from this NCA acoustic steel spring coupling. And as it is clear, we have progressing dynamic stiffness for both cases, but the acoustic steel spring coupling is very much slower, has a very much slower increasing dynamic stiffness than the silicon elastomer coupling. And we see this especially here, for example, at 4% twist amplitude. The acoustic steel springs coupling's dynamic stiffness is at about 135%, whereas the silicon coupling has more than 220% dynamic stiffness. As we already heard today, we know that elastomer couplings are highly dependent on temperature, age, static preload frequency, and as well as decreasing twist amplitudes. And so if we look at this graph, we see a curve that is based on measurements where we had varied the static preload from 50 to 90% and also from 10 Hertz up to 25 Hertz. And we see that this does not affect the dynamic stiffness of the coupling, only a decreased twist amplitudes has an effect. So in order to do a quick summary of this acoustic steel spring coupling, we had single springs and distilted tangent, which means we have very low friction and therefore also a very slowly increasing dynamic stiffness, which means that this coupling is not only soft when loaded with nominal torque, but also stays soft when loaded with very small vibratory torque, and therefore it is preferred for acoustic applications. So let's conclude this part, and now we move on from acoustics to standard torsional vibrations and to a coupling with higher friction, which is, for example, applied to a genset application where we probably have a problem by very high resonances during engine run-ups. And in such a case, we would need very high damping values in general, and so also a high friction damping would be beneficial. So how to get this high friction damping? We can compute this by using the undimensional damping factor kappa. And we have here two formulas to compute this kappa for, in the first case, for a dual spring design, and on the second case, for example, for 4 springs per pack. And we see that these formulas are pretty much the same, except from one multiplicative constant here and an additive constant here highlighted. And if we now compare these constants, we can see easily that kappa for a 4 springs per pack is higher than for a dual spring design. And from this we can easily conclude that we have higher friction damping due to the fact that we have more springs per spring pack and therefore more friction between the springs. And if we applied this to the design strategy, we had here 2 examples. So we can see here on the left side a coupling with 3 conical springs per pack, and on the right side with 4 springs per pack. And this design then gives us the desired additional friction damping. Applying such a coupling then to a genset application, we would get these results. So we see here clearly that the twist angle of the coupling can be decreased significantly when we use a 4 springs per peck coupling here, this green curve, instead of coupling with a dual spring design, which would be here. So higher friction damping in this case is beneficial. So in order, so I want to put a short summary on this whole friction damping topic. First, we had the NCA steel spring coupling with very low friction and slowly increasing dynamic stiffness. And then we had the high friction coupling with its multiple spring design, in contrast to before, and higher friction damping. And if now we want to apply hydrodynamic damping, if someone needs more damping values, we can do this individually and independent of the design of the coupling. So if the torsional vibration calculation shows some very high resonance amplitudes that we want to lower, we can apply this hydrodynamic damping very freely. And for example, for this hydrodynamic, for these acoustic applications, we would apply less hydrodynamic damping than for a genset applications where very high damping values in general are needed. And so we can see here that there are various coupling types, and we have here various designs of the coupling. We have dual springs, we have single springs. Here we have multiple springs designed with 3 springs per pack or 4 springs per pack. And we can not only vary this design, this internal design of the coupling for each application requirement, but also the hydrodynamic damping can be added very individually to gain the desired results. And so it is very important for us at the torsional vibration calculation team to know as many parameters, to know as many information about this application, about the requirements of this application, about the customer's wishes, so that the optimal coupling can be selected and the optimal design and the optimal hydrodynamic damping can be selected. This can be done in terms of downsizing, in terms of acoustics, in terms of, robustness. And so with all that in mind, I would like to thank you all for your attention.